Okay, hello, you're welcome to my channel. Now in this video, we're going to figure out a very big thing here called the tangent problem, right? Good. Well, from the history of calculus, it is this problem, the tangent problem, and another one, the area problem, that brought about calculus, the differentiation and the integration, right? The tangent problem brought about the differentiations, and then the area problem, which I'm not going to consider it here, brought about the integrations. Great. But let's focus on that. Good. But first of all, I'm going to have to start off with somewhere, all right? I'm going to start with the definition of derivative. What do we really mean by the derivative of a function? Okay, this is it. Derivative of a function, let's call that function f of x, all right? I know you may be used to the convention y all the time, but y is the same thing as f of x in this case, as I've stated. So the derivative of a function f of x at a point x naught, all right, of its domain. So for any x value, right, in the domain of that function, what do you mean by the domain of the function is this. At this point x naught, the value of this function, all right, after evaluation, is a real number. So when the value of a function is defined at a point, then that point is said to be in the domain of that function. Great. Now, the derivative of a function at the point x naught of the domain is the slope of a line tangent, all right, to the curve at that point. So you have a function, maybe before this function will become a curve, we must have plotted it on a graph, all right? So I'm going to draw some pairs of axes here, and then the line that is tangent to that curve at that point x naught is called the tangent line, all right? And then the slope of that tangent line is the derivative of that function at that point. Great. So let me draw a pair of axes and show you what I'm talking about here. All right, good. So we have the output axis and then the input, all right? So I'm going to call this output f of x, all right? And then I'm going to call the input x. Great. And now, this is f of x, so to plot that, well, this f of x is just an arbitrary notation. It could represent any function. It could be a linear function, that's just a straight line, a quadratic, a cubic, a trigonometric function, any kind of function at all, right? So what I would just do is just to draw any random structure to represent the function. So it's just going to be any curve, right? That will be helpful to us. Great. So let's say it doesn't just end here. This looks a very crazy curve, but anyway, it's going to be very helpful. Good. And now, let's talk about the point x naught, right, in the domain. So let me come down here and pick this point and call it x naught. Okay, so this is where the point touches the curve. It touches the curve at that point, all right? So maybe you can do some dotted lines up there. Now, what do we have? We have here that, that the derivative is the slope of the line tangent to the curve at that point x naught. So since this is the point x naught, we want to find the line tangent to this curve at this point x naught, right? What do we mean for a line to be tangent to a curve at a point? That is, the line just touches. That's the meaning of tangent, right? Okay, it just touches the curve at that single point, x naught, all right? We do not care if it cuts the curve at some other point. All we care, it just touches. It doesn't cut through, all right? It doesn't cut through like this. It just touches. And this is the way that the line will go. We will draw the lines in this manner to go like this and touches and then go again, all right, without actually cutting through at that point, just touching the curve at that point. Well, this may not really be accurate, but it's a good thing to work with. Good. Great. And now, let's see. Since this is the line that is tangent to the curve at that point, then the slope of the line tangent to the curve at that point will give us the derivative of that function at that point. Good. And now, to find the slope of a line, we always need 2 points. This is where the tangent problem occurs. To find the slope of any line, okay, we will need 2 points on that line. For example, if you have a curve, let's say you're plotting a graph, and it was a linear function, and the function goes this way, just a straight line, right? Then to find the slope of this straight line, you will need to fix 2 points on that line, any 2 points at all, all right? When you fix them, you will now compare the change in the y values over the change in the x values, that is change in y, over the change in x. This gives us the slope of that line. Okay, you can pick any 2 points at all. Even from this point to this point, it will give us the same slope as from this point to this point, right? Because that's just a straight line, it is constant throughout. But the main issue here is that to find the slope of a line, all right, we will need 2 points on that line. But here, to find the slope of this line, right, we are only having 1 point which touches the curve. This other point, this other line, all right, the other part of the line does not touch the curve, right, because from the definition, it only touches the curve at 1 point. Now, how do we possibly figure out what the slope of this line will be, given that the slope of a line will always need 2 points on that curve or on that line? This is what, that is just the tangent problem, all right? Good. Now, to figure out what the slope of this line will be, as I said earlier, we will need 2 points on this curve, not just 1, all right? Great. Suppose I fix 2 points on the curve. We're going to start off with what we know already to get what we do not know. I fix this point of interest. Okay, I'm using it with the red ink now. And I fix it with another point up here, right? Maybe I can call this one P, point P. I call this one point Q. And you know the coordinate of this point will be, maybe let's do this. Let me give it a corresponding output, all right? From this to that line, this is going to be f of x naught, right? Good. That is just the corresponding y value when x naught is the input. Good. We fix another point here, all right? And now, let's see what we've got. We can draw a line that will cut through this curve at these 2 points. And that line is what we call the secant line. So we just draw a line that cuts through the curve, right? That cuts through those 2 points. That line is called secant line, just secant, all right? All right, good. Now, the slope of this secant line is possible to be found, all right? Remember when we talked about rate of change? We can just take this to find the slope of the secant line. We can just take this, the rise, right? The change in the output divided by the change in the input, all right? Okay, but that's just by the way. Now, you notice that this, from this point to this point, the horizontal distance will be measured as, we are going to call this point x naught, and then we are going to have to measure this and give it a name, all right? Suppose this distance from here to this point is h. Let's measure it to be h. And this point is x naught, then this place will be x naught plus h, all right? So that is what I would choose to call that. And again, as x naught was the input, f of x naught is the corresponding output. Now that we have x naught plus h as an input, then the corresponding output will be just from here to here, all right? So maybe we can do this, and then we call that f of x naught plus h. So you observe that when the input is x naught, the output is f of x naught. Now that the input is x naught plus h, the corresponding output will be f of x naught plus h. Very nice, all right? Good. So to find out what the slope of this secant line will be, from this point x naught to this point x naught plus h, we will use the average rate of change formula, right? The same notation, which will give us this, the difference between these two y values, all right? So we're going to have f of x naught plus h minus f of x naught, all right? That is this minus that is this distance, this vertical distance, all right? Okay, and then we're going to also find out what the horizontal distance is from this point to this point. Of course, I called it h already. So maybe just put that down, divided by h. So this is like saying the gradient or the slope, okay, using m to denote the slope of the secant. So that right there is the slope of the secant is given to be that. Remember, our main problem was to find out what the slope of the tangent will be, all right? The slope of this line tangent to this point, to this curve at that point. Well, observe this point. Assuming this point is flexible enough, and we can move it through the curve. We just keep pushing the point through the curve, right? If we push this point here, and we push it up to this point, just by shifting it, okay, through the curve, right? Shifting it, you will observe that this line will be getting towards the tangent line, right? Forget about the rough work. This line will now become like this, to now lie like this, the second line. Okay, so as we are pushing this point closer and closer to this x0, the second line will be coming closer and closer to becoming the tangent line, all right? That means that the slope of the second line will be becoming the slope of the tangent line if this point gets closer to this other point, all right? That tells us if this point gets closer to this point, this horizontal line will be getting closer and closer to 0, all right? Good. Because of that, as the horizontal distance gets closer and closer to 0, this point here, x0 plus h, all right, and that is the coordinate, will be getting closer and closer and closer to this point, x0, right? So to figure out what the slope of the tangent will be, we will be taking the limit. This is the language they brought in. The limit as the coordinate here gets closer and closer to this particular point. Good. So we'll be talking about the limit as this horizontal distance gets closer and closer to 0, right? When it gets closer and closer to 0, you will see that the slope of the secant line will now become the slope of the tangent line, right? So I'm going to say the limit of the slope of the secant as h tends to 0 will give us the limit of this, right? The limit as h tends to 0 of f of x plus h, okay, x0 plus h minus f of x0 divided by h. Good. So since we figured that out, that as the horizontal distance tends to 0, the secant line will approach the tangent line, then the limit of the slope of the secant as h tends to 0 will become the limit of the slope of the tangent as h tends to 0. So this right here is the slope of the tangent just as the vertical line tends to 0. So just as this limit, okay, will have a real value. Great. So that right there is going to be the derivative of that function at that point. Anyway, that is very nice, all right? Now we have a point x0, right? That is just for a single point. We can also use the same thing and apply to another point, x1, right? Just by shifting x1. So for any point at all on the x-axis, this is going to be true. So what I would do here is to replace this x0 with just x. That x denotes for any point at all on the x-axis. If you can find the gradient or the slope of a tangent, the slope of a line tangent to a curve at a point, then at that point, the slope is called an instantaneous rate of change. And that brings about the derivative. Okay, great. All right. Let's apply this right here in finding derivatives of some functions or the slope of a line tangent to a curve. All right. Okay, great. And this is what we'll be making use of whenever we're talking about differentiation from first principle, which we are going to apply in our next video. All right, great. Okay, thanks for watching. Please subscribe to my channel.